Let us now look at cases where you may have multiple optimal solutions. Sometimes a final assignment matrix contains more than required number of independent zero elements. This implies that there are more than one optimal solution with the same total cost assignment. Multiple optimal solutions enable management to exercise judgment and select that set of optimal assignments which is more suited to their requirements. To explain the concept of multiple optimal solutions, let us consider an example. So the example here is that the ABC cab company has a taxi waiting at each of the 4 cab stands. 4 customers have called and requested service. The distance in miles from the waiting taxis to the customers are given in the matrix. We have to find the optimal assignment of taxis to customers so as to minimize the total driving distances to customers. So the interesting thing here is to note that the assignment model can be used to assign taxis to a customer. I mean, this happens very often that you would imagine how are the taxi companies managing to assign taxis and in the most efficient manner to the customers depending on where the customer is calling from. And now imagine that you are a manager of this cab company and you have multiple cabs and you know the locations where those are and you have multiple calls from various customers. So how would you decide that which cab should go to which customer? So if you look at the matrix here, we have stand 1, stand 2, stand 3 and stand 4, and we have A, B, C and D as the customers. Now if you look at the figures, that is the distance in miles, basically the cab standing at stand 1 will have to travel 40 miles to reach to customer A. Similarly, it will have to travel 50 miles to reach to customer B, 60 miles to reach to customer C, and 65 miles to reach to customer D. Similarly, the cab standing at stand 2 will have to travel 30 miles to reach to customer A, 38 miles to reach to customer B, and so on. Now the question here is, how do we assign the cabs to the customers so as to minimize the total driving distances? So let's use the Hungarian method to solve this problem. So the step 1 is to express the problem in an n by n assignment matrix. So let's do that. So step 1, let's copy the matrix. So we have stand 1, stand 2, stand 3, stand 4, and we have customer A, B, C and D. Let's note down the distances. Now let's move to step 2 and subtract the smallest element in each row from every element in that row so as to obtain at least one zero in each row. So let's move to step 2. So let's copy the shell of the matrix. Now in the first row, the smallest element is 40. So let's deduct 40 from each of the elements in the row. So we get 0, 10, 20, 25. Now for the second row, the lowest element is 30. So we get 0, 8, 16 and 18. For third row, the lowest element is 25. So we get 0, 8, 16, 18. For the fourth row, the lowest element is 39. So deducting 39 from each of the elements in the row, we get 0, 6, 12 and 20. Now let's move to step number 3. Here we'll subtract the smallest element in each column of the matrix obtained in step 2 from every element in that column. So let's copy the shell first. Now in step 2, the first column already has 0, so we'll copy it as it is. In the second column, the lowest element is 6, so let's deduct 6 from each of the elements. So we'll get 4, 2, 2, 0. For the third column, the lowest element is 12, so we'll get 8, 4, 4, 0. For the fourth column, the lowest element is 18, so let's deduct 18 from every element. So we'll get 7, 0, 0 and 2. Now let's find out if we have achieved an optimal solution or not. So let's move to step number 4, where we'll find out whether we have reached the optimal solution or not. Now in step number 4, we'll check if we have achieved an optimal solution or not. This we can judge by connecting the zeros by the minimum number of straight lines. If the number of straight lines is less than the number of rows or columns, then the optimal solution has not been reached. However, if the number of straight lines is equal to the number of rows or columns, then the optimal solution has been reached. So let's first copy the matrix that we had achieved at the end of step number 3. So since we have 4 rows and columns, let's first go row wise to see if we have any situation with 4 zeros. So we don't have any row with 4 zeros. Let's do the same thing column wise. Now the first column has 4 zeros, so let's draw a straight line here. Second column does not have, third also doesn't have, and fourth also doesn't have. Now let's again go row wise, and this time we'll check for 3 or more. So we don't have any row which has 3 or more zeros. Let's do it column wise. So we don't have any column with 3 or more. Let's try to go again row wise with 2 or more. So this row has 2. Now let's do the same thing column wise for 2 or more. So fourth column has 2. So let's draw a straight line again. Now we don't have any other zeros remaining, and all zeros have been covered by the straight lines. And the number of straight lines is 3, while the rows and columns is 4. So basically the optimal solution has not been reached. So let's now move to step number 5. Here we'll select the smallest element not covered by the lines and subtract it from each element not covered by the lines. Secondly, we'll add that number to the elements at the intersection of the lines. And third, we'll reproduce all the other elements as is. So let's now move to step number 5. So let's first copy the shell of the matrix. Now from the uncovered elements, 2 is the lowest element. So we'll deduct 2 from all the elements which are not covered by the lines. So let's first do that. So we get 4 minus 2, 2, 2 minus 2, 0, 2 minus 2, 0, 8 minus 2 is 6, and 2 and 2. Second is we'll add 2 to the elements which are at the intersection of two lines. So this element and this element. So we'll add 2 here. So we get 2, and for this element we get 4. And thirdly, we'll reproduce all the other elements as is. So let's copy all the other elements. Now after step 5, let's again find out if we have achieved the optimal solution or not. So let's move to step number 6 and let's copy the matrix. So now let's go row wise first to see if we have any row with 4 or more zeros. So we don't have any row with 4 or more. Let's see column wise. We don't have any columns with 4 or more zeros. So let's now try to go row wise for 3 or more zeros. So the second row has 3. So let's draw a straight line here. The third row also has 3. So let's again draw a straight line here. Fourth row has only 2. Now column wise also there is nothing with 3 or more. Now let's try row wise, but this time we'll search for 2 or more. So first row has only 1. Fourth row has 2. So let's draw a straight line here. First column wise there's nothing with 2 or more. Now let's try 1 or more. So the first row has 1. So now we have 4 straight lines and 4 rows or columns. So basically we have achieved the optimal solution here. Now since we have achieved the optimal solution, let's now try and make the assignments. So let's move to step number 7 and let's copy the matrix. So now let's first assign the rows or columns which have one exclusive 0. So let's go row wise first. So the first row has 1, so we can assign this here. Now since A has been assigned to stand 1, we can't assign A to any other stand. So let's cross off all other zeros in that column. Now let's go for row number 2. So we have two zeros. Stand 3 we have again two zeros. Stand 4 again we have two zeros. Now let's try column wise to find out a column with one exclusive zero. So first column is already assigned. Second we have three zeros. The third column we have one exclusive zero. So let's assign this 0. And since now stand 4 has been assigned to C, we can cross off all other zeros in this row. So let's cross this 0. And column number 4 also has two zeros. So now if we evaluate the situation, we can see that stand 2 and stand 3 both have two zeros for the same columns. So here we don't have any exclusive zeros for stand 2 and 3, and neither do we have an exclusive zero for B and D. So basically we have two options. We can assign stand 2 to B and stand 3 to D, or we can assign stand 2 to D and stand 3 to B. So let's move to step number 8 to see how the two assignments can be done. So our step number 8, let's take the first case where we'll assign stand 2 to B. So let's copy the matrix that we had achieved in step number 7. Now let's assign stand 2 to B. So since B is assigned to stand 2, let's cross off all other zeros in that row or column. So automatically stand 3 is then assigned to D. So in scenario 1, our assignments are stand 1 is assigned to A, stand 2 is assigned to B, stand 3 is assigned to D, and stand 4 is assigned to C. And the distance to be traveled by the cabs as per the original matrix is 40, 38, 43, 51. So the total is 172. Now let's look at the second scenario where we will assign stand 3 to B. So let's first copy the matrix that we had achieved in step number 7. So in this scenario, let's assign stand 2 to D. So since stand 2 has been assigned to D, we'll cross off all the zeros in the same row or column. So stand 3 gets assigned to B. So in this scenario, our assignments become stand 1 is to A, stand 2 is to D, stand 3 is to B, and stand 4 is to C. And the distance as per the original matrix for the stand to customer combination is 40, 48, 33, 51. So the total in scenario 2 is also 172. So in this case you can see that both the scenarios produce the same result in terms of distance. So both are optimal solutions, and it's up to the decision maker to choose any of these solutions depending on their preference.